All right, so here we have another relative frequency problem, don't we? So let's read the problem here. In a worldwide study of counterfeit US bills, bills from 30 large cities were analyzed. The results are the following. 175 of the bills were verified as counterfeit, while 218,955 were not counterfeit. So we're going to select a bill at random and check it to see if it's counterfeit or not. Okay. What is the chance or the probability, or some of you like the notion of percentage, what is the percentage of counterfeit bills, US bills, in the world? And those of you who have traveled in many places, US bills are more than welcome, aren't they? Okay. So you'll find US currency all over the world. And if it's not used, you can exchange it for local currency, all right? But anyway, here's our situation. We're going to take a relative frequency in order to find the probability, aren't we? And our numerator will be the event that a bill selected as counterfeit. Okay. Excuse me, 1 second. Okay. All right, so what is the denominator here? Well, the denominator is the sum total of all the bills. In this problem, we're told that the numerator is 175. That's the number of counterfeits. And the non-counterfeits are 218,955. So all we have to do is add up the counterfeits with the non-counterfeits, and we get the denominator of our relative frequency, right? So let's do that. If we add up the complements, the counterfeits and the not counterfeits, put those numbers into your calculator, and you get 219,130, 219,130. Now, can anybody tell me what the denomination of those counterfeit bills typically are? A $1 bill, a $5 bill, a $10 bill, a $100 bill. What do you think they are? Anybody? Can anybody tell me what? Just guess it.
Hundreds.
The hundreds. The hundreds are the ones that are typically counterfeited. Okay. Although some of us have experienced a time when we went into a store, a convenience store, whatever it is, and we give them a 20, and they look at it, inspect it. So apparently the 20s now are popping up as counterfeits as well. Okay, so now we're done, right? We've got the numerator, we've got the denominator, so we take the ratio, and it's a small number, right? If you calculate this fraction on your calculator out to, I've got it here out to 6 places, it's about 7.99 times 10 to the minus 4. Now, in your algebra class, you've studied what scientific notation is. So all I've done is I've taken my fraction and I've converted it to scientific notation, okay? And you know the rules for scientific notation. Your number in scientific notation is typically a number between, strictly between 9 and 10. Sorry, 1 and 10, okay? And the idea is to place the decimal point after your value, your leading value, which in this case is 7. Okay. And now you adjust for decimal and remember to multiply by the correct power of 10. Now the power of 10 may be positive, it may be negative, depending upon whether you shift your decimal place to the left or to the right. Left makes it positive, shift it to the right, you'll go negative, you'll have a power of 10 to a negative power. And that's what we have here. So if I count 4 places to the right here and place my decimal point after the 7, which is that leading coefficient, then I get it in scientific notation. Now, when you read reports in the newspaper or a magazine, they may report a number in scientific notation. And typically, those numbers, again, refer to probably a fraction, like we've done here. Now, for us, the fraction is perfectly fine. If you get a problem like this on the exam, your fraction is golden. You don't need to write it out as a decimal or as a decimal in scientific notation. Most publications will typically write out a number like that in scientific notation, but that's not necessary for this worksheet, okay? And then here is another way to write this, right? We can write this as a percent. And I typically, when you look at percents, 2 decimal places suffices, right? So 0.08% would be a rounding of this number, either as a decimal to 6 places or written in scientific notation, okay? So this number has been expressed in percent. Now, let's take a look at that number. It's a pretty small number, less than 1/10 of a percent, right? 0.08 of a percent, okay? All right. Any questions about the relative frequency of a counterfeit bill, a US bill, in circulation worldwide? Okay. Now, in this problem, we're told that the value of total US currency in the world is about $1.55 trillion. Okay? Now remember, thousands is 10 cubed, millions is 10 to the 6th, and billions is 10 to the 9th, and trillions is 10 to the 12th. Go to Google and you'll see a table of terms for thousands, millions, billions, and trillions, okay? 10 cubed, 10 to the 6th, 10 to the 9th, 10 to the 12th, okay? So when I did this problem, you see here that the likelihood is about 0.08% of selecting a counterfeit bill, if the total value of bills circulating worldwide in US currency is about 1.55 trillion, then all we have to do is multiply, right? Multiply the chance of selecting a counterfeit bill times the total value, and that'll give us the value of the counterfeits. So let's do that. Okay, so if we multiply our probability or the percentage of counterfeit bills times the total value of all currency, US currency out there in the world, then we get the value of the counterfeits, don't we? Okay, so this is more of an algebra problem than a statistics problem. Statistics comes in because we have a percentage here or a probability of counterfeit. Okay, now this multiplication up here is done in the following way. I convert my probability or my percentage to scientific notation, and I convert this big number, 1.55 trillion, in terms of exponents of the power 10. And as I just mentioned, a trillion is 10 to the 12th. Okay, so we're going to multiply 7.99 times 10 to the minus 4 times 1.55 times 10 to the 12th. Okay, and when we do that, when you multiply powers of 10, you just add up the exponents to get the product. So a minus 4 with the positive 12 gives us 10 to the 8th. And now we're just multiplying 7.99 times 1.55. This dollar sign, it's okay to put it out in front. We could stick it in here and in front of the 1.55 if we wanted to, like I did up here. Okay, all right, so now we're reduced to multiplying 7.99 times 1.55. And if you put that in the calculator, you'll get this number. Okay, you'll get this number here. And so 7.99 times 1.55 is about 12.3845. So there I've rounded it to 2 places. And you still have your factor of 10 here, 10 to the 8th. Okay, and all I did here was move the decimal place over to the left 1 place, and so that's putting it in scientific notation. 1.23845 times 10 times 10 to the 8th. 10 times 10 to the 8th is 10 to the 9th, which is billions. So we get $1.24 billion, which is a big chunk of money, isn't it? A lot of money out there. So it's no surprise that when you go into the mini mart, the clerk is checking your $20 bill. Okay, all right. Any questions about numbers 1 and 2? Okay. Here you use probability to get your relative frequency, your ratio or your percentage. And down here, you just multiplied the percentage times the total currency, and that'll give you the value of the counterfeits, right? Okay, any questions about 1 and 2? These are mostly algebra problems, aren't they? We did a little bit of numerical organization using scientific notation, but and it's useful because it we don't have so many decimal places going on all the time, okay? But that's your choice. The important thing for you to realize is that you're using a probability idea here, and that you're taking the percentage of currency of the counterfeits in order to get that value, okay? So make sure you see the mathematics behind this more so than the, let's say, the cosmetics of putting numbers in scientific notation. This is typically how professional journals would treat their large numbers like this. Large and small numbers. We got a very small number as the probability, and then the currency was a very large number. The value of the currency, okay? All right, now we switch gears here, and now we're going back to probability, okay? And in this problem, let's go ahead and read it. Nokia supplies mobile phones in lots of 25, and they have reported a defective rate of 0.075%. It's a pretty small number, as you would imagine. The manufacturing process is pretty reliable in most cases. However, 10, 15 years ago, when mobile phones started to become more commonly in the marketplace, then we did see some defective items. Some of you remember 10 years ago when you bought a cell phone and it didn't work, you had to take it back, right, and get a new one, a phone that worked. Has anybody given their phone back lately because it was defective? Any defective phones out there? Okay, so 10 years later, these phones are more reliable, but they're a lot more expensive, aren't they? Okay, I think the last phone I bought was almost $1,000. So, when you pay that amount of money, you would expect it to be very reliable. Okay, so we're going to do the following, okay? If a control engineer, a quality control engineer wants to, okay, there was one question up here that I didn't read out. What is the probability of an individual phone being defective? Well, this sounds a lot like number one, where we have a percent defective. We're looking at a lot of, let's say, 25, okay? So if we multiply the percentage times the number 25, we should get the number of defectives in a lot of 25. 70.075% is the probability, right? Okay. So that's really what we're interested in. What is the probability of an individual phone being defective? Okay, it's given right here to be 0.075%. All right. Okay, now we'll modify that number a little bit by dividing by 100, and that'll take away the percent, give us an absolute decimal value. Okay, we'll do that in a second here. Now, if a quality control engineer wants to carefully analyze a defective mobile phone, what is the probability of her getting at least one defective phone in a lot of 25? Okay. And we'll come back to the final question here. This is more quality control. This is the protocol that the manufacturer might use for quality control. Okay, So as I just said above, up here, a probability of a defective is 0.075%. Okay. Or, as I said, if we divide by 100 to take off that percent sign, we get now the absolute probability of 0.00075, right? If you multiply that number by 100, you get the percent, 0.075%. Okay. Now, this notation up here, I'll come back to that notation. But what I want you to understand here, which is a very useful point of view, we'll use this point of view in many of our calculations in probability, okay? So all we're going to do now is use coin tossing as a model for her inspection procedure. That is, the probability of selecting a defective or the probability of seeing a heads in a coin toss, let's call it 0.00075. So imagine that we're tossing a coin, all right? Or in this problem, imagine that the engineer has selected a phone and she wants to know the probability that it's defective. What's probability of the heads? It's 0.00075. Now, she's going to inspect each of the lot of 25 phones. So to model that, we're going to say, okay, she's going to toss the coin 25 times. Now, the inspections are considered to be independent. In other words, the fact that she checked a phone, found it to be non-defective, has no bearing on the quality of the next inspection. It's like coin tossing. If you get a heads on the first toss and you ask, what's the probability of a heads on the second toss, it's going to be 0.00075. So it's like independent coin tossing. So we're going to toss the coin 25 times, and we're going to ask for a probability here that in this inspection process, out of 25 tosses, she gets only one defective, okay, or at least one defective. So we can find the probability of one defective, all right, and then take the complement, which is at least one defective, and subtract that probability from 1. So we're using your ideas here that you've learned about coin tossing and the idea of taking a complement of an event to calculate the probability of an event. So if the event is A, the complement of the event is A prime, the probability of A is 1 minus the probability of A prime. So those are the two ideas that we've got going here that we've already covered in previous worksheets. The notion of coin tossing, toss the coin n times, in this case n is 25. The probability of the defective, or the probability of the heads, is 0.00075. Before, when we were using a coin, our probability of success, or the probability of the heads, was 1/2. But in this model, the probability of success, which is selecting a defective item, is 0.00075, quite different than 1/2, right? Okay, but it's the same reasoning. We're tossing a coin n times with the probability P of a heads P may be any number between 0 and 1, okay? For coins, we usually use a half. But in other models, it may differ from a half. It may be close to 0, maybe close to 1, okay? And it may be any other intermediate value in the interval from 0 to 1. Okay, so now in the line here shaded in yellow, I have a equation in terms of x, which is the number of defectives that she selects. Think of x as the number of heads in 25 tosses of a coin. Remember, we studied that random variable when we set n equal to 3. Okay, and so here's the first key equation, and I want you to understand this equation. Okay, we want the probability that she gets at least one defective. Okay. All right, so what we're doing here is taking the probability that x is greater than or equal to 1. Remember, x counts the number of heads and end tosses, and in this model and in this problem, the number of defective items that are selected in a lot of 25. Do you see the model, how the model is adjusted to this problem? It's really just the coin tossing model. 25 independent tosses of a coin, and we want to count up the number of heads, and in particular, we want the event that the number of heads is at least 1. Okay, so that's greater than or equal to 1. X is greater than or equal to 1. Okay, so this is the first mental hurdle that you have to jump, right? Is why are we looking at this probability here? Okay, that embodies the event that there's at least one head in the n tosses, the 25 tosses. There's at least one defective in the 25 inspections. Okay, and we know what the probability of a defective item is. Okay, now we use our notion of complements. What's the complement of at least one? Well, it's none. Okay, if there are no defective items, that's the complement of the event that there was at least one defective. Okay, so all we have to do is calculate the probability that there are no defectives, subtract that from 1, we get the probability of the complement, which is that there is at least one defective. All right. Now, this notation here, after the negative sign here, okay, this notation here, we'll come across this notation again when we talk about the binomial distribution. Remember, I mentioned very much in passing that the coin tossing experiment is a binomial distribution. That variable x has a binomial distribution. Now that distribution comes up in chapter 5 in great detail, and we haven't gotten to chapter 5 yet. So I want to argue, okay, in the following way. In order to get one defective, okay, then we would have to let x equal to 0, and that's assuming that all of the choices that we made in the 25 inspections resulted in defective, okay? And then we'll subtract that from 1. Okay, so here, all right, So in other words, what's the probability of getting all heads in your 25 tosses, right? Okay. And notice that the probability of the heads is P. Okay. So if you don't want any heads and you want all tails, you're going to multiply the probability P to the 0th power. That means that no head appeared, and then all of the rest of them that you selected were non-defective. Okay, which would be this probability here. Okay, and that gives you this number here turns out to be 1. This is the number of ways that you can permute the 25 non-defectives. Okay, and we'll come to that next chapter. All right. And some of you probably said, well, right here, I can calculate the probability of no defective items, right? Okay. That just means I got 25 tails, which is 1 minus P raised to the 25th, all right? And you get this value here. Okay, this number is 1. Okay, we'll come to that number next week. Okay, that's 1. And then we multiply the probability of a non-defective, which is this difference here, raised to the 25th. In other words, what's the probability of getting 25 tails? If we get all 25 tails in our 25 tosses, then the complement of that is that we get at least 1 heads. All right. And so if we do the calculation on the calculator, okay, we do this calculation on the calculator, we get 0.019. Okay, just put this into your TI-36X Pro, and that'll handle this calculation very easily. And we get about 2%, right? 0.019 is about 2%. So the probability of selecting at least 1 defective phone out of a lot of 25 is about 2%. Now, 2% in some senses is a good number, right? Okay. All right, so at least 1 defective item, 2%, it might be within the threshold that the quality control engineer can be confident that she'll select a defective item, at least 1, in an inspection of 25 phones. All right. Now, we'll come back to this problem again. All right, not exactly in this format, but we'll see this problem again. And we'll use a binomial distribution, which is given in StatCrunch. Okay, we can calculate these numbers in StatCrunch as well. And we can answer questions about binomial experiments. These are often called Bernoulli experiments, where you have independent trials. The probability of success on each trial stays the same, and it's a number P between 0 and 1. Okay? However, in this problem, we don't really need the binomial. We could probably go from right here to right here. Okay? Okay, 0.99925 is the probability of non-defective. And in order to get 25 non-defectives in your draw, okay, you would just raise that probability to the 25th power. Because remember, the events are independent, the tosses are independent, so you just multiply the probability together, all right? Okay, now, as a little bit of background, in order to really understand this problem, go back to your coin tossing where n was 3, where you toss the coin 3 times and calculate the probability that you get no tails, okay? Or can we do that right now? What's the probability of getting a tail? Remember, the probability of success here is 1/2 in the coin tossing. So what's the probability of seeing a tail on the first toss? What's that going to be? Sadie, can I ask you to step up? Sadie?
Yeah, I'm here.
What's the probability of a tails on the first toss?
50%.
Good. All right. Now, what's the probability of seeing 2 tails in 2 tosses?
0.25.
Right. And how did you derive that?
0.5 multiplied by 0.5.
Exactly. The events are independent.
Yep.
And you did this problem in your previous worksheet, right?
Yeah.
When 2 events are independent, all you do is multiply the probabilities. And then finally, what's the probability of getting 3 straight tails?
So then you multiply 0.25 with 0.5 again.
Yes. Okay. So 1/4 times 1/2 is 1/8, or 0.125. So the probability of getting all tails is 1/4
0.125.
times 1/2,
Yeah.
which is 1/8. Let's keep it as fractions.
Oh,
And
okay.
then the probability of at least one head is 1 minus 1/8, right? Or 7/8. And remember from your frequency table, the only occurrence of no heads when you got all 3 tails, which was 1/8. So the probability of at least 1 head is 7/8. This is the same thing here. The probability of at least 1 defective is the probability of drawing a non-defective 25 straight times, and then we subtract that from 1, and that'll give us the probability of at least 1 defective. Okay, so there's a lot going on in this problem, and the important thing is to understand that you can use the coin tossing model to solve this problem. All right, later we'll use the binomial distribution to amplify this model to cover a lot of situations. For example, an opinion poll. Survey N voters in the population. What's the probability of getting a certain number of voters in favor of the proposition? That's like coin tossing again. Okay, that one might be a little tricky because voters talk to each other, don't they? They might influence each other's opinion. Or a writer in a newspaper may write an op-ed in order to influence the voters one way or the other. So, you know, we might say that there's some conditional probability going on between voters. So your job as a opinion pollster is to make sure that your sample is independent, that you don't get too many influencers. Has anybody come across that word now, influencer? I think that's a new word to our dictionary. But there are lots of people out there who are trying to sway your opinion one way or the other. And certainly those have an effect. And of course, as an educated voter, you want to read and synthesize and try and understand an issue before you answer yes or no. Okay? All right. that's all I've got for today. Our office hour will start at 11:30. So I'll end the meeting. Let me check your chats here if there are any questions from the audience. Okay. Okay. All right, we're good on the chats. Any questions about your assignment, about your problems here? It's a nice mix of algebra and geometry. Algebra and probability. No geometry, sorry. Okay. All right. Okay, are we good? Questions? Going once? Going twice? Okay, guys, I'll come back at 11:30 if you have any questions. One other note here. MyLab statistics. Okay, let me just show you what I have here. Can you see this? Okay. I've enrolled 28 students. So several of you have not enrolled yet. I did extend the enrollment date to the end of the month. So hopefully you'll all get enrolled. And then in a week or two, I'll share with you the progress and make any comments about your progress. This is week 5, and our last day of class is December the 14th, Monday, December the 14th. So that sounds like a lot of time, okay? But you know, time flies, right? So what I'll do is in a week or two, I'll check on your progress. And if it goes beyond October 1st and you haven't enrolled in MyLab statistics, then I have to drop you from the class. There's no way that you can pass the class without those resources, okay? All right, guys, let's, if there aren't any questions, I'll end the meeting. Okay. All right, so see ya.